In this video and the following videos, we will take a closer look at small molecules and how we can represent them numerically in a similar way as we have done it for proteins. But first, let us take a look at what molecules are and what their building blocks are. Small molecules are low molecular weight compounds consisting of a few atoms. They are the simplest units of chemical and biological function, often serving as the building blocks for more complex structures. All molecules consist of atoms that are linked to each other via chemical bonds. For example, in the image on the right, you can see a molecule consisting of carbon and oxygen atoms that are bound to each other in a specific configuration. So in order to understand what molecules are, we will shortly have a look at what atoms are. There exist more than 100 different atoms, or to be precise, there are 100 different atoms that can be found naturally or synthesized on Earth. However, in biomolecules, only a small subset of these atoms are typically present. These atoms are carbon, oxygen, hydrogen, nitrogen, phosphorus, and sulfur. And I put the colors that are typically used to represent the different atoms in brackets behind the atom names. So we see that, for example, in our molecule in the top right corner, we have carbon atoms represented in gray and oxygen atoms displayed in red. So let's have a look at what atoms are and how they differ from each other. Every atom consists of three different types of subatomic particles, as you can see in this image: the protons, the neutrons, and the electrons. The protons are positively charged particles found in the center of the atom in the nucleus. The number of protons in an atom defines the element. For example, carbon has 6 protons. Then we have neutrons, which are neutral particles, which means they do not carry any charge. Neutrons add mass to the atom and can vary in the number among atoms of the same element, creating different so-called isotopes. This variation does not affect the chemical properties of the element, which are primarily determined by the number of protons and electrons involved. However, for most elements, the number of neutrons is typically the same as or slightly more than the number of protons. And then we have the electrons, which are negatively charged particles that orbit around the nucleus in so-called electron shells. Electrons are much smaller than protons or neutrons and carry much fewer mass, but they carry the same amount of charge as protons, but of opposite type. While protons have positive charge, electrons have negative charge. The electrons of an atom play an important role in chemical reactions and for generating bonds between different atoms. On the next slide, we will have a bit more detailed look at that. So, what do we have so far? At the heart of every atom is its nucleus, a dense core where nearly all the atom's mass is concentrated. This nucleus is composed of two types of subatomic particles, the protons and the neutrons. Protons carry a positive electrical charge, while neutrons are neutral, having no charge. The number of protons in the nucleus defines the chemical element. For example, all carbon atoms have 6 protons. While the number of neutrons can vary, leading to so-called different isotypes of the same element. Surrounding the nucleus are electrons, negatively charged particles that are arranged in layers or shells at various distances from the nucleus. The distribution of electrons in an atom's electron shells is crucial for determining an atom's chemical behavior and its ability to form certain types of chemical bonds with other atoms. On this slide, we're going to look at what electron shells are, and we're going to do this in a somewhat simplistic way, but this will be enough to get an understanding of how atoms form bonds with each other. So let's start with a short definition. Electron shells are layers or regions around the center of an atom where the electrons of the atom are placed, and electrons are arranged in these layers in a specific way. Each shell can hold up can only hold up to a certain number of electrons. The first shell can only hold up to 2 electrons. The second shell can hold up to 8 electrons, and the third shell can in principle hold up to 18 electrons, but in all cases that are relevant for us, this shell is usually only filled up to 8 electrons as well. And if this shell is filled, there are even more shells that can be filled. So how are those electron shells filled? First, the innermost shell is filled with electrons until the shell is full, and then the next shells get filled with electrons. As you can see in the example of our carbon atom in the top right corner, the first shell is filled with 2 electrons, and then we start to fill the next shell with electrons. Here we have 4 electrons, which means that the second shell could take 4 more electrons before we would start to fill the next shell. Atoms generally aim to fill their outermost electron shell because a filled outer electron shell leads to atoms that are more stable. More stable means that it has lower potential energy and is less likely to react with other substances. Higher stability is a favorite state in nature, and this is why atoms strive to fill the outermost shell. Atoms have different options to achieve this, including the following. Atoms can either gain or lose an electron if this then results in a filled outermost shell. However, this does not simply happen spontaneously in isolation. It typically requires another substance that can accept or donate the corresponding electrons. Another option is covalent bonding. Atoms can also achieve fuller outer shells by sharing electrons with other atoms, forming covalent bonds. The sharing can involve multiple atoms, sometimes leading to complex molecular structures, or it can only involve 2 atoms. This type of bonding is of particular interest for us since it explains how the atoms in the small molecules are bound to each other. Let's have a look at how covalent bonds can be formed. How can 2 atoms share electrons such that they both have filled outer electron shells? Let us, for example, look at hydrogen. In its most common form or isotope, hydrogen has 1 proton and 0 neutrons in its nucleus, and it has 1 electron orbiting the nucleus. The nucleus is here simply displayed as a black circle in the middle. The first electron shell is represented by the gray circle around the nucleus, and the single electron is displayed in white. Let's imagine we now have a second hydrogen atom that also has a single electron in the first shell. From the previous slide, we know that those hydrogen atoms would like to have 2 electrons in the electron shell in order to be more stable. To achieve this, they can share the electrons in this shell. We see that through sharing the electrons, both hydrogen atoms have now electrons or 2 electrons in their first shell and are more stable. We see that the electron shells have to be overlapping and the 2 atoms form a bond, a so-called covalent bond. Since the 2 atoms share 1 pair of electrons, we call this a single bond. We will now look at atoms that can share even more electrons to achieve full electron shells. Here we have oxygen atoms. Oxygen atoms typically have 8 protons and 8 neutrons in their nucleus and 8 electrons orbiting the nucleus. You can see that the first electron shell is filled with 2 electrons and the second shell has 6 electrons. But to be more stable, and to fill the second shell, it needs 2 more electrons. To achieve this, it can share electrons, for example, with another oxygen atom. In order to fill the second electron shell, it is not enough to share only 1 electron pair, but instead they need to share a total of 4 electrons, which are 2 electron pairs, 2 coming from each atom. Since they share 2 pairs of electrons, the resulting bond is called a double bond. Double bonds are stronger than single bonds, but they are not simply twice as strong. On this slide, you can see 2 nitrogen atoms, and nitrogen atoms typically have 7 protons, 7 neutrons, and 7 electrons. This means there are 2 electrons in the inner shell and 5 electrons in the outer shell, which means nitrogen needs 3 more electrons to fill their outer electron shell. To achieve this, nitrogen atoms can share 3 pairs of electrons with another nitrogen atoms, which results in a triple bond between the two atoms. As a result, both atoms have 8 electrons in their outermost electron shell, while sharing 6 of these. Up to now, I only showed you that we can have covalent bonds between two atoms of the same type. But we can also have covalent bonds between different atoms and also involving more than 2 atoms. In this image here, you can see a carbon atom that we already have seen on an earlier slide. Carbon atoms typically have 6 protons, 6 neutrons, and 6 electrons, which means that carbon atoms need 4 additional electrons to fill their outer electron shell. In principle, quadruple bonds consisting of 4 electron pairs exist, but carbon atoms cannot form quadruple bonds with another carbon atom. The reason for that is due to some details about the electron shells that we do not discuss here. However, carbon can form single, double, and triple bonds with other atoms to fill its outer electron shells. For example, it can bind to 2 oxygen atoms to form carbon dioxide, CO2. With each of the oxygen atoms, it can share 2 electron pairs. As a result, the carbon atom as well as the oxygen atoms have filled outer electron shells. Alternatively, a carbon atom could also bind to 4 hydrogen atoms or to 1 nitrogen atom and to 1 hydrogen atom to fill its outer electron shell. So far, we have only seen very simple small molecules consisting of at most 3 atoms. However, in many small molecules, we have many more atoms that are bound to each other, such as in the image on this slide. So we need a way to represent the structure of small molecules. This means if we have a small molecule we want to encode, which of the atoms in our small molecule have covalent bonds between each other and what type of covalent bonds do we have? Do we have single, double, or triple bonds? And we also want to know the spatial arrangement of the atoms. As you can see in this image, the atoms are not simply arranged in a 2-dimensional plane, but in a 3D space. And we want to be able to encode the arrangement of the atoms in a 3D space. In the next video, we will look at how we can achieve this.